Hi everybody, this video covers section 2.5 and we will be talking about exponential functions. Specifically, we'll be talking about the graph of the exponential function, its properties, this thing called Euler's number, which is denoted by E, and then in a follow-on video we will talk about applications. So you are all familiar with this particular function, I hope. It is the square function. It's f of x is equal to x squared. And this is what its graph looks like. It's basically a parabola whose vertex is at the origin and it opens upward. Now, what would happen if we swapped out the x and the 2? Well, then we would have f of x, or g of x, is equal to 2 to the x power, and this is what we have. And this is an exponential function. A couple of things that you will notice is that this particular function is always going up. It's always increasing. And also, every different value of x will produce for you a different output of the function. Unlike the square function where -1 and 1 would produce for you the exact same value. This is not a one-to-one function. This is a one-to-one function. And then finally, this number, 2, or whatever this number happens to be, is called the base of the function. And yes, the x is called the exponent of the function. Now, if the base happens to be greater than 1, like what we have here, then we will always have an increasing function. If the base is a number between 0 and 1, the function will always be decreasing. We will never have a base that is 1, because if we do, it will actually be a constant function where y is always equal to 1. So it's not really all that interesting, and we are not going to deal with negative bases in this particular course. So the base will always be a positive value that is not equal to 1. If it's greater than 1, it will be an increasing function. If it's less than 1, it will be a decreasing function, but it will always be a one-to-one function. Specifically, every value of x will produce for you a different value for the output. Okay, so this is our formal definition for the exponential function. And that is that f of x is equal to b raised to the x hour, where b is any positive number that is not equal to 1. Again, b is called the base. And as you can see here, the domain, the values that you can put into the function, are any points on the real line. So they're all real numbers. And the range will always be positive numbers. It will never, ever reach 0, although it will get arbitrarily close, as you can see here. And it will always increase all the way to infinity. So domain is the entire real line. The range is all positive numbers. Now, also what you can notice that there are 3 important points when we are looking at exponential functions, and they are somewhat helpful in determining what the value of b is for that particular function. And these are the 3 points. The first one is -1, 1 over b. Now, if b is greater than 1, then this point will be less than 1. If b is between 0 and 1, then this point will be greater than 1. And I believe that one of the things that you're probably noticing here, actually, we'll talk about that in just a second. Now, the second point is the point 0, 1. Every exponential function, unless it is shifted or scaled in some way, will always go through the point 0, 1, where x is equal to 0 and y is equal to 1. And then finally, the third point is 1b, where the x-axis is equal to 1, and then the y-axis would be equal to the base. And with that in mind, you can almost determine what 2 functions we actually have here. Notice here we have 1 and we have b. So it turns out that b is probably equal to 4. And indeed, that is correct. This right here is the exponential function f of x. F of x is equal to 4 to the x power. When x is equal to 1, f is equal to 4. Now for this one, it's a little trickier. And it turns out that for the blue one, this one does not really help you with it, because 1b is this point way, way, way down here, and it's very difficult in this graph to determine what it is. But -1, 1 over b can actually help you. Notice that when f is equal to -1, or when x is equal to -1, we have 1 over b. So this would be, let's do something like g of x or let's say g of x, is going to be equal to b raised to the x squared, but when g is equal to 1, or negative 1, sorry, we will have, we have the point 4 raised to the negative 1 power. And what does that tell you? Well, that actually tells you that b here is equal to 1/4. And we would have that g of x is equal to 1/4 raised to the x power. Okay, and of course when x is negative 1, we have 4. So if you have a decreasing function, you want to look at this value to determine what the base is. And if you're at 4, then the base is going to be 1/4. And then if you have an increasing function, you want to look here to determine what the base is. Okay, what else can we say about this? Every graph will always contain the point 0, 1. You can see that right here. All graphs are continuous, and basically what that means is that when you try to sketch the graph, you never have to pick your pencil off the page to do that. There's always a horizontal asymptote, which is the x-axis, and that basically means that the graph always gets very, very close, but never actually touches the x-axis. If b is greater than 1, then the graph is increasing. If the b is between 0 and 1, the graph is decreasing. Here is theorem 2, and this gives you some of the properties of the exponential function. And here we're going to assume that a and b are positive, they're actually going to be bases, and that they are not equal to 1. So we're basically saying that a and b are bases, and x and y will be real value numbers. Okay, and we have a number of laws that apply here. And here's the first one. If you, and I'm going to write these out because I think it's more intuitive than me just showing this to you. If you have a to the x times a to the y, same base, that is equal to a to the x plus y. And that is actually what we call the product property of exponentials. Furthermore, if you have a to the x divided by a to the y, we can write that as a to the x minus y, and this is the quotient property. And this, of course, is the product property. Now, if you have something that is a to the x power raised to the y power outside of a grouping symbol, then since the y is outside of the grouping symbol, these will multiply. This will be equal to a raised to the x times y power. And we actually call that the power property. And the other two are distributive properties. Basically, if we have the product of two bases, a and b raised to the x power, that is the same as a to the x times b to the x, or in the quotient sense, a divided by b, all that raised to the x power. That's nothing more than a to the x divided by b to the x. And of course, you can't do the x minus y here because if you'll notice, they both have different bases. The other thing is that since the exponential function is a one-to-one function, then the statement a to the x power is equal to a to the y power is only true if x is equal to y. So if this statement is true, if a to the x equals a to the y, then x equals y. Similarly, if x equals y, then a raised to the x is equal to a raised to the y. That is one powerful property of a one-to-one function, which you will take advantage of in your homework. And then finally, if x is not equal to 0, then a to the x can only be equal to b to the x if and only if a is equal to b. If a is equal to b, this is true. If this is true, then a must be equal to b. All right, now we have one very special number that appears a lot in exponentials, and that is Euler's number, and we tend to call it e. It turns out to be the most commonly used base in exponential functions. And one of the main reasons why it's very commonly used is because it's very easy to work with when you're in calculus. It's also an irrational number. And what does that mean? That means it cannot be written as a ratio of two integers. It is something that has decimal places that go on and on forever. However, it can be approximated like this. And for large value for large values of x. And for the first 12 decimal places, this is pretty much what it looks like. Usually if I'm writing out e, I just use the first three and be done with it. And we tend to say that f of x equals to e of x, or e to the negative x, are known as the exponential functions. All right, so here's the big question. So what? Why do we particularly care? Well, it turns out that exponential functions model a number of physical things, such as the growth and the half-life, particularly for radioactive materials such as uranium and whatnot. It's also can be used for monitoring the depreciation of a certain item. That also follows an exponential function. It turns out that if you ever took a course in network analysis or queuing theory, the length of the communication packages entering a switch, or the amount of time it takes for a switch to actually send that packet out, tends to follow an exponential distribution. And also, if you had a velocity, if you had the velocity of an object in constant thrust or with constant acceleration in a not in a vacuum, but in basically an environment with air, or where the resistance of air is considered, always follows an exponential function. As a matter of fact, if you jumped out of a plane, then your velocity as a function of time would be equal to 128, which is basically your terminal velocity, times 1 minus e to some constant. I forgot what that is. I'm just going to call it negative alpha t. And if you were going to plot this, this is what it's going to look like. Here's my graph, more poor representation of it. There we go. Well, when t is 0, you have 1 minus 1, and you have 0. And then your velocity will increase, and eventually it will level off at 128 miles an hour, which, by the way, is what we would call the terminal velocity. And that's what that equation would look like. And as I mentioned before, they're used to model not just capital depreciation, but also compound interest instruments, which you will learn in gory detail in our next chapter. Now, I want to conclude this video with a couple of examples, and most of these examples portray what you will find in your homework. And here we need to match each graph with its associated equation. Now, notice here that we have f of x is equal to a 1/4 raised to the x power, g of x is equal to 5 to the x power, h is equal to 4 to the x power, and k is equal to 1/3 to the x power. Notice that f of x and k of x or the base for f of x and k of x are less than 1. That means that those functions are going to be decreasing. I'm trying to get my pen back up there. There we go. So this one will either be b or d. And this one will either be b or d. Furthermore, here we have bases that are greater than 1, so these will be increasing functions, which are these two. So these will either be c or a, and this will be c or a. Now remember, I told you the important points are negative, when x is equal to -1, right there, when x is equal to 0, which really does not help us in this case, or when x is equal to 1. And I also mentioned that if you have an increasing function, you want to look at the value when x is, we want to evaluate the function when x is equal to 1. So let's take a look at when x is equal to 1. When x is equal to 1, g should be equal to 5. All right, so here's 1. Let's go all the way up. There's 5. G has to be C. It cannot be A. Why? Because when G is equal to 1, or when X is equal to 1, G is equal to 5, and we have a 5 there. Okay, cool. So then that implies that the next one would hopefully intersect 4. Let's find out. Here's 1. Go all the way up. There is 4. So A must be the graph of H. So we can get rid of C here. All right, so notice how for the increasing ones, we could use this point. For the decreasing ones, we want to use -1, and the reciprocal of whatever we find on that graph will be equal to the base. And what specifically do I mean by that? Well, let's take a look at f equals f of -1. F of -1 is going to be equal to 1/4 raised to the -1 power, which is going to be equal to 4. All right, so here's -1. Let's go all the way up and notice there is 4. So D is the graph for that particular function. Okay, evaluating at k when x is equal to -1, you will have 1/3 raised to the -1 power, and that is equal to 3. Okay, so here we go. Here's -1, go all the way up. Notice this graph right here intersects 3, right there. So in this case, B is the graph of K. And that is how you would approach that particular problem. Example 2, we are given a function. And apparently we're going to have f of x, which is where it's defined between -2 and 2, and we want to choose the correct graph. Now notice that -2 and 2 is telling you that x is going to be greater than or equal to -2 and less than or equal to 2. And we can use that information to help us choose the correct graph. All right, now take a look at this one. This one starts at -2 but only goes to 0. So basically the domain of this particular graph is not that, it is -2, 0. This cannot be the graph. Also mention that we know that an exponential function is a one-to-one function. So every value of x, every different value of x will produce for you a different value of y. Well, notice that when x is equal to 1, that's what y is right there. When x is equal to -1, f takes on the exact same value. This is not a one-to-one function. All right, moving on. Notice here, so it's either going to be this function or this function, but notice that we have something which is less than 1. The base here is strictly less than 1, which implies that we should have a decreasing function. I'm running out of space. Sorry about that. This is an increasing function. That one is out. This, of course, is decreasing. This is the function we're looking for. So if you're in MML, you click on this and you're happy. Okay, and here we have a similar thing. Here we have f of x is equal to -3 to the x power, and we need to choose the correct graph. Now, one of the ways that you can look at this is f of x is equal to 3 raised to the x power times -1 or taking the negative of. So what we have is 3 to the x multiplied by -1, which is a reflection across the x-axis. So you actually, so to solve this problem, the next one, you actually need to use some of the information that you learned in Chapter 2. So we have a reflection across the x-axis. So since 3 to the x is always positive, -3 to the x is always going to be negative. It cannot be this graph. It cannot be that graph. Okay, now let's look at our important point, which in this case is going to be x is equal to 1. All right. When x is equal to 1, 3 to the x is going to be equal to 3. Or -3 to the x is going to be equal to -3. Maybe a better way of looking at that is like this. F evaluated at 1 will be equal to -3 raised to the first power. Well, remember your order of operations. What's the first thing you do? You do the exponents. Well, the grouping symbols. Then you do the exponents. So 3 to the 1 power, hey, that's just 3. So we just have negative 3. So f evaluated 1 is negative 3. What do you have here? Well, probably negative 1/3, but basically you don't have negative 3, so this can't be it. Here, when f is equal to 1, or when x is equal to 1, f is equal to negative 3, which is what we're looking for. This has to be the graph. Okay, next one. Well, this one's even more fun, and here we still need to apply a little more about Chapter 2, or the beginning of Chapter 2 to figure this out. So here, we have f of x is equal to negative 4 plus e to the 1 plus x power. Or if I wanted to, I could write this as negative 4 plus e to the x plus 1. Why did I do that? Well, because when we've talked about shifting, we've always looked at it this way. Now, remember what we talked about when we talked about relative to vertical shifting. If we add something outside of an argument, like the this would be the argument of an exponential function, we have a vertical shift. So let's just pretend that we have this function g of x, which is equal to d of x. All right. Well, then essentially, what we have here is that f of x is equal to negative 4 plus g to the x plus 1. Remember, g is equal to d of x. All right. This right here is a vertical shift of negative 4. Okay, so vertical shift down by 4. This right here is a horizontal shift to the right. Since we have a plus sign, it is a shift to the right. Okay, so if you're going to plot e to the x, it would look something like this. Because remember, e is about 2.718. So e to the x is about 2.718 raised to the x power. It's an increasing function. It's going to look something like this. It's going to cross 1 here, and then 2.7 stays right about there. It's going to go up like that. That should be just straight down there, but it's kind of hard to do the drawing pad. So what we're going to do, what's happening is that this curve is going to be shifted down vertically by 4. So instead of its horizontal asymptote being the x-axis, it is going to be shifted down by 4, and it's going to be down here. Okay, so it's all going to be down here. And with that in mind, take a look. Could this be the graph? Well, this could not be the graph because this one actually has its asymptote at negative 1. This could not be the graph because its asymptote is at 4. Now, this could be the graph, but notice that, remember, e to the x, it's always an increasing function. This is decreasing. This cannot be the graph. And what about this one? Well, this most likely is the graph. Okay, because notice here we have an asymptote. We have an asymptote of negative 4. But what else could we look at? What about if we looked at f of negative 1? That would give us negative 4 plus e to the 1 plus negative 1, or 1 minus 1. And that would give us negative 4 plus 1, because that would be e to the 0, which is 1, which is negative 3. When x is negative 1, y is negative 3. That has to be the graph. So the best way to work with this graph is to see how the asymptote shifts, and notice it's shifted down by 4, and also to find that value of x, which will cause this exponent to go to 0, which gives you something pretty straightforward to figure out. Okay, we have a few more examples here, and here is the next one. Here we want to solve the equation for x, and we have 8.5 raised to the 5x minus x squared is equal to 8.5 raised to the 6th power. And how the heck do you solve something like that? You solve that by taking advantage of the fact that f of x is a one-to-one function, or the exponential function is a one-to-one function. So if this statement is true, then the exponents have to be equal. So based on the fact that this is that the exponential function is indeed a one-to-one function, if this is true, then it follows that 5x minus x squared is equal to 6. So we just need to work. We just need to solve this equation. Unfortunately, we have a quadratic, but it may not be that bad. Let's basically move all this stuff over here. And if we do, we will have that 0 is equal to x squared minus 5x plus 6. Okay? Now, if you remember from 114 or previous classes, the way that we solve this is basically by finding factors of 6 that sum to negative 5. And I think we can find an obvious one, and that would be negative 3 and negative 2. Negative 3 times negative 2 is 6. Negative 3 minus 2 is negative 5. And that means we would have that 0 is equal to x minus 3 times x minus 2. And that, if that's the case, there are two solutions. One solution is x is equal to 3 and x is equal to 2. And the way you would enter that in Hawks, in MML, I forgot which application or which courseware I'm working with, is basically 3, 2. And that should be all you need to put in. And the next one is this one. Solve the following equation for x. Well, notice here we have x e to the negative x plus 8 e to the negative x is equal to 0. And here we're taking advantage of the fact that the exponential function is never, ever 0. This will never, this term and this term will never equal 0. Not only that, these two terms are common factors, which means they can be factored out, just tantamount to using the distributive property in reverse. So let's go ahead and do that. We can write this as e to the negative x times the quantity x plus 8 is equal to 0. And what we can do is we can multiply both sides by e to the x. Because once again, it never reaches 0, so there's no reason why we can't do this. These will cancel. That just is equal to 1. E to the x times 0 is just 0. So we will have 0 is equal to x plus 8. And then to figure out x, we can just subtract 8 from both sides. Minus 8 there. Minus 8 there, and then we would have x, these cancel, we would have x is equal to minus 8. And that is all that I have for this particular video. Stay tuned for a follow-on video that will go over the application phase of this particular section. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.